Hi, I'm Arup, a PhD student at the University of California, San Diego, and a Lawrence Scholar at Lawrence Livermore National Laboratory. So my presentation topic is the fast and energy efficient next generation non-volatile memory-based SSD architecture. So let's start with what is emerging non-volatile memory all about. So recently we have seen phase change memory and spin transfer torque memory. They are very promising and are projected to have DRAM-like performance and high density and low standby power. And their potential usage as a DRAM replacement and fast storage. Do you have this one? Oh, OK. Oh, big green. OK, so this is the present system architecture where basically have seen flash-based SSDs connect to the host system like Fusion IO, Virident. They are almost 100 times faster than disk for random read or write access. And if this trend continues, we can see this next generation non-volatile based memory attached to PCI bus, and they are even faster. But let's see what's the problem with this next generation non-volatile memory. So one problem is there's a high latency and block interface of PCI. And otherwise, huge software and driver overhead from PCI and as well as the software driver. We measure it on our system, and we found out about 60% of time I spend on software driver and PCI. So it actually destroys all the gain from this next generation non-volatile memory. So we need to eliminate those overhead. So we propose a new architecture for next generation non-volatile memory, which is based on computation close to storage. We basically moved data and IO-intensive applications to the storage so that you don't need to transfer the data from host to storage and back and forth. We expect a huge power and performance gain for that. And also the processing scales as we connect more and more SSDs of this kind. So now let's see the architecture. So this is like PCM-based SSD architecture, which connects with the host using PCI. And there is IO scheduler, which basically receive a read or write IO request from the host and transfer it to PCM controller and send the response back. So we extend this with a storage processor, which connects to each of the PCM controller so that it can operate on data stored over there. And then we connect to the network so that it can communicate with other PCM controller as well and the storage processor. And we modify the scheduler so that it can send the computation request, not only read and write IO requests, as well as it sends some computation request over there. Now let's zoom into the storage processor, which has a control processor, which basically communicate with the host and send data or compute requests to the compute kernels. So this is the control processor. Next component is DMA engine, which basically loads the data from storage and load it to the local memory. Compute kernel basically holds your application-specific code, so you can employ any application over there. So we built this on B3 FPGA prototype system, which has PCI 1.1 to connect to the host. Our system runs on 250 megahertz, and we build all the hardware components in FPGA. And to demonstrate the effectiveness of this approach, we implement Smith-Waterman algorithm, which is commonly used in many bioinformatics applications. And let's see the results. So we compare with different storage technologies, such as Red Disk, Fusion IO. Moneta is a PCM-based conventional SSD, and with Maverick. So we achieve almost 19x speed up as compared to disk, and 4x speed up as compared to conventional PCM-based SSD. And about the energy efficiency, we get around like 6.5x more energy efficient than Moneta. And this attributed to like a reduction in data transfer between the host and storage, and better utilization of NVM memories and efficient data processing in the SSD. And finally, conclusion. So that's all.